You ever wonder how an AI tackles a problem that's just so ridiculously complex it make your head spin? Well, you might be surprised to learn that sometimes the answer is a trick it's shockingly simple. And it's brilliant. But, and this is a big but, that simplicity, it comes with a pretty serious flaw, a hidden catch that we're going to dive into.
Okay, to really get this, let's start with a little thought experiment, a puzzle. So picture this. You're standing somewhere in this huge, sprawling mountain range, but you're completely trapped in a fog so thick you can barely see your own hands in front of your face. Your one and only goal is to find the absolute highest peak in the entire range. So, what do?
The real problem here, of course, is the fog. You don't have a map, there's no satellite view, no bird's eye perspective. All you can possibly know is the little patch of ground you're on right now and maybe a few feet around you. And believe it or not, this exact limitation, it's what AI is up against all the time when it's dealing with these gigantic, messy problems.
So, what's the most logical move? The most intuitive strategy? Well, you'd probably look around at your feet, right? You'd feel out the ground, find the direction that seems to go uphill the steepest, and you'd take one step. Just one. Then from that new spot, you do the exact same thing again, and again, and again. You just keep climbing.
So this really simple, almost common sense strategy, it actually has a name. It's called hill climbing, and it is a core fundamental strategy in artificial intelligence. It's how AI finds good solutions to incredibly hard problems without ever needing to see the whole map.
All right, so to really understand how this whole hill climbing thing works, we first need to get our heads around how an AI sees the problem. And the way AI scientists think about it is as this vast, invisible landscape.
This landscape has a technical name. It's called the state space. Now, just imagine for a second that every single possible answer to a problem, I mean every single combination, every possible configuration, is one tiny little point on this landscape. Now, some of those points, some of those solutions are terrible. They're way down in the valleys. And some of them are great. They're way up high on the hills.
And this image here makes that idea super clear. Take a look. The bottom axis, the horizontal one, that's all the different possible solutions laid out. That's our state space. And the vertical axis, that's what we call the objective function, which is just a fancy way of saying the score. It tells us how good each solution is. So the higher the altitude on this map, the better the solution. And the goal? The goal is to find the single highest peak on the entire map, the global maximum.
Okay, so we've got our landscape of possibilities. Now let's set our little climber loose, the hill climbing algorithm, and see exactly how it finds its way around this place.
The entire idea is captured perfectly in this one simple rule. Go uphill along the steepest possible path until no farther up. That's it. It's what's known as a greedy approach, and that's a key word here. It's greedy because it's only focused on the immediate, short-term gain. It always makes the move that looks best right now, with absolutely zero thought for the bigger picture or any long-term consequences.
So let's break that down, step by step. First, the algorithm just starts at a totally random point on the landscape. Second, it looks at all of its immediate neighbors, all the spots it could take just one step to. Third, it figures out which of those neighbors has the highest altitude, and boom, it moves there. And finally, it just does this over and over and over again until it gets to a spot where every single neighbor is downhill. And at that point, it stops. It thinks its job is done. Okay, I know this whole landscape and climbing thing is a pretty cool metaphor, but what does this actually look like when an AI is solving a real problem? Let's use a classic AI puzzle to make this way more concrete. Here we go, the famous 8 queens problem. The challenge is simple to state, but hard to solve. Place 8 queens on a regular 8x8 chessboard in such a way that no 2 queens can attack each other. So, in our metaphor, every single possible arrangement of those 8 queens, that's a single point on our solution landscape. So, how in the world do you measure altitude on a chessboard? Well, we use something called a fitness function. It's just a score. For this problem, we'll say the score is the number of pairs of queens that are not attacking each other. With 8 queens on the board, there are 28 total pairs of queens. So a perfect score, the highest peak on our chessboard landscape, would be 28. Okay, let's actually watch this algorithm in action. We start with the board you see on the left. Right now, the AI is thinking about moving just one queen to try and improve things. Now, look at the image on the right. It shows the fitness score for every possible next move. Our current board has a score of 17. Not great.
The AI scans all the options and sees, hey, I can move and get a score of 18 or 19. Wait, I can even get to 20. So what does it do? It makes the greediest move. It picks the best possible step, the steepest climb uphill, and moves that queen to the square that gives it a fitness of 20. Just like that, it took one step closer to solving the puzzle.
So far, this seems awesome, right? It's simple, it's fast, and it clearly improves the solution with every single step. But remember our climber in the fog? That simple strategy has a massive fundamental blind spot. Think about it. The algorithm is only ever moving uphill. But what happens when it gets to the top of a hill? I'm not saying the tallest mountain in the range, just any old hill. It gets stuck. That's what happens. This is the big flaw, and it's called a local maximum. Look at the diagram again. If our little climber makes its way to the top of that smaller peak on the left, well, every single step from that point is downhill. And since its only rule is only go up, it literally has nowhere to go. So the algorithm just stops, completely satisfied, thinking it has found the best possible solution. And this is the absolute crucial takeaway. Hill climbing is not guaranteed to find the best solution, the global maximum. All it guarantees is that it will find the top of whatever hill it happened to start on. And this really brings us to the central paradox of this whole approach. It's a really powerful and useful AI tool, but you can never be 100% sure that the answer it gives you is the absolute best one out there. So let's lay it all out. The pros? It's lightning fast and incredibly efficient with memory because it only has to remember where it is right now, not the whole journey it took to get there. It's also really simple to implement. But the cons? Well, they're big. It has that fatal flaw of getting stuck on small hills. Its success or failure depends entirely on its random starting point, and it gives you absolutely no promise that it will find the best answer. So if it's so flawed, why do people even use it? That's a fair question. And the answer is because for a ton of real-world problems, we're talking about things like scheduling every single job in a massive factory or designing the layout of a super complex computer chip. Finding the one single perfect solution might literally take a computer billions of years to calculate. Hill climbing, on the other hand, can find a good enough solution in minutes. And in the real world, a good enough answer now is almost always better than a perfect answer, never. And that really leaves us with a pretty fascinating thought, doesn't it? At its heart, hill climbing is all about a trade-off, perfection versus speed. It's a reminder that sometimes the smartest, most pragmatic approach isn't to search forever for that one single highest peak, but to just quickly find the top of the closest hill. And it makes you wonder, right? When you think about your own life, how often do you do the exact same thing?